Hello and welcome back to the course on machine learning. Today we're talking about the upper confidence bound and the intuition behind this algorithm of the reinforcement branch of machine learning. So let's get started. As we discussed previously, the problem we are solving is the multi-armed bandit problem, where you've got 5 or more or any number of slot machines and you can bet your money in any one of them, and you need to find out how to bet to maximize your returns. And basically we agreed that behind every machine there is a certain distribution, and that's because you don't know which of these distributions is optimal. You need to combine exploration of these machines with their exploitation in order to find out which one of these machines is the best, and then you can start exploiting that one. And the modern application of this problem is, of course, advertising. So if you have 5 or 10 or 50 or 500 different ads, how do you find out which one is the best one? Of course, you can run just an A/B test and then use the results of that, but that means you're doing the exploration and then you're doing the exploitation separately. You're going to incur lots of costs. You're going to waste a lot of time. We want to combine exploration and exploitation and get to the optimal result as soon as we can and maximize the output of our efforts. All right, so this is a quick summary of the multi-armed bandit problem. So let's go through this very quickly so we can get to the fun stuff. So we have D-arms. For example, arms are ads that we display each time a user comes to a web page. Each time an ad is displayed or a user visits this page, that's a round. For each round n, we choose which ad to display to the user. You can only display one ad, like with the one arm bandits. You can only pull one of those arms. You can only choose one machine to bet on. At each round n, ad I gives a reward, whether it's a 0 or a 1, and basically Ri of n is equal to 1 if the user clicks on the ad, and 0 if the user didn't, and our goal is to maximize total reward we get over the many rounds. So that's basically what we're doing. And this is how the upper confidence bound algorithm works. And I won't go into too much detail on this because actually Hadlan is going to run you through this, and you're going to code this from scratch in R, and you're going to code this also in Python in the following lectures of the course. So we're not going to spend time on this. We're actually going to get to the essence of the algorithm, right? So let's get to the intuition part, which is how does it work? What's actually happening in the background when this algorithm is running? All right, so let's have a look. These are our slot machines or one-arm bandits, and each one of them has a distribution behind it. We want to find the best one, right? Looking at them, we can't tell which one it is, but let's see we do know. Let's see we know the end result. Just for argument's sake, what would it look like? Well, this is, for instance, in this case, these are the distributions behind those machines. You've got, the machine. This is how they're spitting out the results with these distributions. And just by looking at this, you can tell right away which one is the best machine. Which one would you bet your money on constantly? If you were playing, it would be this one, right? So right away here, you can see that this one has the best return, and you would want to just all the time just bet on this one, and your outcome would be the best. But we don't know that, right? We don't know that, and we want to find that out in the process of playing these machines or using those ads that we're running, and find out which one is getting the most clicks. We don't have the time and money to do that exploration before the actual campaign is running. We want to do that in the process. We want to maximize our return already from the very start. So how do we do that? Well, let's transfer these distributions or the actual expected return from these distributions onto a vertical axis. So we're going to take these values and we're going to put them onto a vertical axis over here. So there's our vertical axis. So for distribution 1, let's say the value was there. For distribution 2, there was a value. We remember it was lower. Distribution 3 even lower. Distribution 4 higher, and distribution 5 the best, right? So those are the expected values or returns for each of those distribution for each of those machines. That's why our y-axis. But again, we don't know that. So how does this algorithm work? Well, it assumes some starting point. For every distribution, it just assumes that there is a certain starting value that, okay, let's just assume that because we can't distinguish, we can't discriminate against these machines in any way, they all look the same. Let's assume that they all have the same return, and let's put it on that level. Now, then what the algorithm does is those formulas that are behind the algorithm, they create a confidence band, and it is designed in such a way that with a very high level of certainty, that confidence band will include the actual return, or the actual expected return. So basically, the first couple of rounds are going to be trial runs. So we're going to intentionally just try out the machines at least one time each in order for us to be able to place this value here and come up with a confidence band which is going to be very large. So at the very start, it's very large, but it is designed specifically in a way that the expected value, which is this one over here, with a very high level of confidence, falls inside this confidence with a very high degree of certainty, falls inside this confidence bound, which is built around this red empirical value which we have derived. And at the very start, it's all the same, right? So, and then how does this algorithm work? Well, out of all of them, we pick the machine with the highest confidence bound. Right now, it can be any of these machines, right? They all have the same confidence bound. We're talking about the upper confidence bound. That's why the algorithm is called the upper confidence bound. And so we're just going to pick any one of them because it doesn't matter which one we pick. Again, we don't know these colored lines. We don't know about them. All we see as the agent or as the person analyzing this, we only see these boxes, and they're all identical to us. So we just pick any one of them. Let's say we pick this one. So what happens next is we actually pull that lever of that machine, and something happens, or we place that ad, right? So we display that ad next, and we want to see, did the person click on it or did the person not click on it? And in this case, the person didn't click on it, right? So it went, this red value goes down because now we have another observation just for this machine that is added to the whole sample of observations for this machine, and the value goes down because, always this red value is like the observed average. The observed average is going to, according to the law of large numbers, is always going to, in the long run, is going to converge to the expected return, or expected average, or expected value for this distribution. So therefore, it is very likely that this value is going to go down. And now, because we have an extra observation, the second thing happens is the confidence interval, did you see that? Confidence interval becomes smaller, simply because we have an additional observation. Of course, it doesn't become that much smaller, but this is just to illustrate a point. Because we have an additional observation, we are more confident in our predictions. We are more confident in everything that's going on. So the confidence interval slowly starts to shrink. All right, so the next step is now we find the next one with the highest confidence bound. So obviously it's not this one, it's one of these four. Just pick any random one. There we go, this one. Do the same thing. So again, the ad is displayed, a person either clicks or doesn't click, and that affects the average that we've measured so far, the empirical average, or you've pulled the lever, you've got a certain, you either won or you lost, and that affects your empirical average, this red line. And as expected, it slowly starts to converge over like lots of iterations. It'll start to converge to the expected value. So it comes closer, and right away you can see now this machine is all of a sudden above all of the other machines, right? So if this was the end of this iteration, that's it. We would assume from here that this is the best machine, and we'd start exploiting it, and therefore this algorithm would be completely useless. But we shouldn't forget about the second thing that happens. The second thing that happens is that because we got an additional observation in our sample now, we are more confident in this interval, and these confidence bounds, they're designed. Their only purpose is to include the actual expected value wherever it is. We don't know where it is, but they are telling us that this value, this green value, is somewhere inside this box. But because we got an additional observation, we're more confident. Our sample size is larger, so we're more confident in the overall picture for this machine, so the confidence bound decrease. And now, as you can see, it's no longer the top machine because even though it went up, the confidence bounds went down. So now we're going to look for the next highest confidence bound. It can be any one of these three machines. And just look at any one randomly for now. This one, and here, even though the red line is above the blue line, so according to the law of large numbers, you'd expect this to converge to that. But sometimes it can randomly occur that it can go the other way, right? Things can happen like this. It's all probabilities. So basically, it might even go up. So there we go. It went up, even though the blue line was below the red line. It can happen as a, like as a just as per chance, right? In the long run, it will converge, but on a random occasion, it can go up. It can go in any way. And again, we got another element in the sample, so the confidence bands converges. Okay, so we kind of get the picture of what's going on here. So now we're going to pick the next one with the highest upper confidence bound. Let's say this one. Then we do the trial, we do the round. What happens? Does the person click on add? Do we win money from the slot machine? And it goes down. Probably not. We didn't click on the ad, didn't win money from the slot machine. So the average of our observation goes down, comes closer to the expected value, and the confidence bounds also decrease. Okay, now we're in business. We can now all of them are kind of starting to play. Next one is this one. Okay, this is now, because we know the end result, we know that this is the best one, right? We know that this is the best ad, or this is the best slot machine we should be using. But like, because just we were kind of like given this insight just for argument's sake or for the purpose of this exercise. But the person that's performing this algorithm, or the algorithm itself, doesn't know that. So unknowingly, it's actually starting to exploit the best option right now. So again, okay, it goes up, good, confidence band goes down, and as you can see, it's still the best one. All right, so now we're going to do it again. We're going to use this one again, and it comes closer, but the confidence bound goes down. Again, this is all just for illustration purposes. Of course, it's not going to go down by that much just because of one observation, but we don't want to be sitting here through 1,000 iterations. This is just to demonstrate the overall picture. So even though we exploited the best option, by exploiting the best option, we're decreasing the confidence bound, which gives an opportunity, or by exploiting any option, if it keeps going up, it keeps being good, because we're building up the sample size, this gives an option to the other, it gives opportunity to the other options or machines or ads to have a chance in the play, so that we're not just, we're not biased towards which one we think is the best or optimal outcome, optimal machine. So now that we move on to this one, same thing, comes closer, bounds decrease, move on to this one, bounds decrease, and we move on to this one, and bounds decrease, and then again this one, bounds decrease, and again this one, might jump closer, bounds decrease. And even though we were very close to finding the solution, that's that one, the bounds decrease so much, and you'll actually see this in the practical application, the practical tutorials that are following, that sometimes we'll, after using the optimal option for some time, the algorithm will still switch to a suboptimal option just because the bounds are decreasing all the time. And then we'll use this one, bounds will decrease, and now we're back to the best one, bounds decrease, and then we're just going to be exploiting this one and exploiting this one and exploiting this one because we found out that it's the best one. So that is, in essence, the whole concept behind this upper confidence bound algorithm, and that's how it solves the multi-arm bandit problem. It's a very interesting solution, much more sophisticated than just selecting randomly or running an A/B test and then selecting the option that won. So if you're in advertising, or if you've got campaigns, or if you come across problems that are similar to this, always just remember about the upper confidence bound algorithm, and you can apply this in your work as well. Very powerful algorithm. And on that note, I hope you enjoyed today's tutorial. In the next couple of videos, Hadelan will take you through the programming of this algorithm, both in R and in Python, and you'll get your takeaway templates. And I can't wait to see you next time when we'll be talking about the Thompson sampling algorithm. And until then, enjoy machine learning.